Appreciate the opportunity. Oh, some of you may notice in the schedule, my colleague Mandar Jog was unable to make it, but he sends his regards and he assisted in the development of the talk. Let's get started. So we're going to talk about today defining a service mesh. Then we're going to turn to some of the best practices for your service mesh that you should be thinking about as a user or as a developer of a service mesh. For users, it's particularly important to think about these best practices before you begin your service mesh journey. Yeah, let's go. So this talk starts like almost every other talk that we've had today with defining a service mesh. And I've been surprised by that. We didn't coordinate our slides. Like I didn't preview everyone else's talks and go, oh, I better make sure to get a service mesh definition in up front. Instead, I think that this is a product of where we're at in the industry today. In spite of the fact that service meshes have been available in various forms for about 4 years now, still very early in, I think, the software lifecycle, or maybe even the fad lifecycle, you might call it. Service mesh is a very hot topic today. And what I hope to show is that one of the reasons it's so hard to define what a service mesh is that explaining a service mesh to someone who's in a DevOps role is like explaining water to a fish. Service meshes are everywhere. They're everything. And so the question is, are you sure that this thing is real? It sounds a little bit like vaporware. You're promising all these buzzword features. What is this thing? Well, I hope that this definition can aid a little bit in clarifying what a service mesh is, both for us as developers as well as for our users. The first thing that everybody talks about when I get asked, what is a service mesh, is microservices. And if their eyes don't immediately gloss over at that compound word, then they probably understand that microservices involve a bunch of services cooperating together over the network, usually using HTTP communication with one another. Usually they're implemented in multiple languages, and there's all kinds of dependencies between them. So that's a bunch of services. And this grid here looks a lot like a mesh. Is this a service mesh? It's a little unclear, isn't it? Well, certainly when we get to a little bit of a more older or more enterprisey style architecture, the N-tier architecture, where each layer communicates only with the adjacent layers. Some of you might be familiar with MVC or MVVM or MV something else. Certainly these aren't a service mesh, right? You've only got 2 network connections involved in the N-tier architecture. Well, I've worked in N-tier architecture, and I've worked in large enterprises owning these sorts of apps, and the truth is that in production, I've never seen one that looked like this. Not once. At the very minimum, an N-tier architecture looks a little bit more like this, where you've got a load balancer handling client connections into your front end, which then has a load balancer to your application layer, which then has a load balancer to your data layer. Maybe you want to be able to do canary deployments at one or all of these layers, so you might have multiple versions of that layer running simultaneously. The load balancer has to be aware of that. Is this a service mesh? Well, there's a lot more gray lines on this diagram now than when we started. Maybe it is. Certainly, the monolith is not a service mesh, right? There's not even one gray line on this diagram. There are 0 gray lines. Not a service mesh at all. I think we can all agree with that. But again, I've never actually seen anything that looked like this in production. If you have, I would love to hear about it. It sounds fascinating. In real life, what I've seen looks a little bit more like this. You know, your clients sit behind a load balancer that connects to multiple instances of your monolith. Hopefully you have enough traffic to need to scale out horizontally, right? That's what we all hope for, is success for our software projects. And hopefully if you're scaling out horizontally, you're not storing state directly inside your application. Things are going to be painful if you do that, so you probably have a data layer. Now our monolith has, 9 gray lines in its diagram. And actually, over time, even if you started out with a monolith, it ends up starting to look maybe a little bit more like this. If your company happened to go through a recent acquisition, and now you have someone else's code in someone else's language on someone else's framework that needs to run in your data center under your rules with your load balancer and probably, hopefully, collaborating in some way, meshing with your monolith. Additionally, this is the web age, so third-party web integrations abound. I don't need to give you examples of this. You all know how many times that you have to integrate with other services out there, exchange data. Well, now our monolith has become the most complex networking diagram that we've seen today. Maybe this is a bit of a misnomer. Is this a service mesh, though? It's certainly a mesh of services. Do you already have a service mesh? Is that what we're talking about today? Well, I think it is, and it isn't. And hopefully that answer becomes more helpful than it sounds right now. When we talk about a service mesh product, what we're talking about is how to manage change across the service mesh that you really already have, the mesh of services that are already your problem. Everybody knows this for microservices. Everybody talks about it. The example is overdone, so I'm not going to spend much time on it. That's every place you need to touch. All of those orange circles are a place that you need to touch in order to make one simple change across your service mesh in a microservices environment. Here's all the places you have to touch to make a change across your N-tier environment. And here are the places you have to touch to make changes across your monolithic environment. The truth is, service mesh products are about helping you with the service mesh you already have today. That's what we're all here to talk about. For a concrete example, let's consider what my boss, Sean, just presented about needing to migrate to MTLS, right? Your CISO heard about a software intrusion, or maybe heard about zero trust at one of the buzzwordy conferences he likes to go to, and now your problem is you've got to implement this across your database, your monolith, that other guy's monolith, the third party that's on the internet that you don't even control, and your client-side load balancer, or not client-side, but your front-facing, client-facing load balancer. This is a huge task. You could spin up an entire team just to implement MTLS across this monolithic stack that was supposed to have been so very simple. So what have we learned here? If we do the math, over time, hopefully, your application grows in complexity. You add on business cases, or maybe add on businesses to your company. And so the number of nodes in your application grows. The number of edges in your application grows. And if you have to address every single one of those nodes in order to make a reasonable change, what you have is, as Tim Hawken coined, I think yesterday at the KubeCon Rejects conference, a service mess. Your ability to respond to change is going down over time. Your investment in just operating your application, this is not development time. This is just day-to-day management, responding to pages. It's going up and up and up. So how do we gain control of this mess? Well, a service mesh provides an interface to the mesh of services that you already own. That means rather than addressing every single one of those nodes individually, taking all of that painstaking time, you are instead addressing the mesh as a whole. In the service mesh, your mesh is ephemeral. You can't address it directly. With a service mesh, it makes that physical. It makes it a first-class citizen that you can control. So we've defined a service mesh now in terms of what it does, and I think that is the most useful definition. What does it do for you? But there is also the question of what is it? What's its form, not its function? Well, I think, as far as I can tell, every service mesh implementation that I've seen has some sense of division between a data plane and a control plane. And there are a lot of options for how these data and control planes are run. It's really not my goal here to get into the comparative analysis of which one of these options is better or worse. But roughly, you can run your data plane as a sidecar, which captures all network traffic from the payload and mutates it. You can run a node agent that sits outside of your pod and captures all the traffic and mutates it. Netflix has a great library called Hystrix that if you happen to be using, I think it's Java, correct me if I'm wrong, provides some great service mesh-like features without the need to run a separate process, which is great. gRPC is beginning to do the same thing. You can run your service mesh sidecar as a black box, as in it captures all the traffic no matter what, and your application has no idea. Or you can run it as a white box, where it listens on a very particular port, and your application can selectively send traffic to the service mesh or not. The control plane, in turn, is responsible for applying the changes that you request to your data. The data plane handles the data. The control plane allows you to control. It is really the interface. And again, within control planes, there's a lot of variability. Some of them some of them are run as monoliths. Some of them are composed as microservices or subservices. The key is that you just need your control plane to be run. A lot of people worry about, well, which cluster is my control plane in? It just needs to run and have access to data planes. If you're running a control plane and you have access to the information you need from the data plane, you can have your service mesh. If you wanted to run it on a VM, run it on a VM. Bare metal, good luck. Some control planes actually also are basically just files. If you look, I think Hystrix has a great example of how to run their APIs just from config files. Your control plane can be as simple or as complex as your use case for it. And so with that in mind, we have these service mesh best practices. Run copies of your control plane in different regions for HA. Distribute your application across zones for HA. Always use MTLS. Never use MTLS with self-signed certificates. Use your service mesh for canary deployments. Use your service mesh for green-blue deployments. It gets overwhelming so quickly. And the terminology just becomes unintelligible as we get deeper and deeper. I'll highlight this one here. Use your service mesh advice to isolate yourself from peers. That's my favorite service mesh best practice. It's very easy to get lost in the maze of best practices, especially as you start trying to compare between products. So what we need is a conceptual model for how to think about service meshes, any service mesh, regardless of the way that it's implemented, that can help us understand how that service mesh will help us meet our needs as users. And so that's the goal of this talk. I'm going to propose that we think of service mesh topology in 3 primary dimensions. You need to think about how you're going to scale your control plane, how you're going to scale your clusters, and how you're going to scale your meshes. And we're going to talk about these not as architectural primitives, but as ways, as means to an end, ways to implement the 3 goals that we have in mind with service mesh, which is going to be high availability for your app, making sure that it's running on compute in many places, resiliency for your app. Is it hard to break this thing? And strong trust guarantees. So let's get started talking about the control plane. The first way to scale your control plane is to run multiple instances of it, whatever it is. Whether it's a bunch of microservices or not, running multiple instances is sane. It allows you to tolerate failure in a single instance. You can do this just on one single system with multiple CPUs, or you can scale these instances across zones and regions where they're going to have a little bit more latency between them. But it's important to notice that this is not the same as multiple logical control planes. The config that they're operating on is still represented by this one nice generic database icon. You have one logical config operating multiple instances of your control plane, and you've achieved some level of high availability because of that. You can also scale your control plane logically. This is a way for you to isolate your configuration so that changes that a user makes are not going to immediately bring down the entire service. You would bring down half, which, okay, maybe scale it 3 or 4 times and bring that number down a little bit. But the point is, by running multiple config stores and multiple control planes, reading from those stores, you now have the ability to roll out a change over part of your network, not all of your network, and to test that change, and then to expand the change into the other logical control plane. There's a question mark in this diagram because we do need something to manage moving us from the one instance to the multiple, from the one logical control plane to multiple logical control planes, reconciling that config between those storages. And we've heard about multiple products today that will assist you in that journey. The next dimension that we want to talk about scaling your service mesh is clusters. This is how you scale compute. This helps us meet the objectives of high availability and application config isolation. Notice I'm not saying service mesh config isolation, which is a separate topic that we just covered with how you scale logical control planes. With multi-cluster, you're able to separate out your application into distinct compute environments. Oftentimes, this is what's necessary in various public cloud environments in order to achieve true regional distribution of your application. You'll need to run multiple clusters. And so with geographic distribution, you have the whole data center can go down. The whole state could go down. The eastern seaboard could go down. And your application will still stay available because you're using multi-cluster deployments. You can also do cost-based routing here. For instance, in this example where we have 2 clusters serving service B, the service for one is one service. It's important to note that. And service A can selectively call service B locally, which is likely to be the most inexpensive networking call. Or if service B in cluster 1 is for some reason overwhelmed or flat out down, service A can communicate with cluster 2's service B using a service mesh. It's important, though, that we respect the namespace and service naming equivalents in multi-cluster. If you have the same service name and the same namespace name in 2 clusters that are part of one mesh, they are one service. You can route to them separately using geographic load balancing. You can think of them separately in some ways, but you have to remember that a given request for service B could be served in cluster 1 or cluster 2. This also provides some isolation for your operators. If you're giving someone access to cluster 2, notice they cannot change the operational paradigms or the operational rules and configuration for service A. One thing to keep in mind, and a few people have called this out, if you have this model, if you have this need as a user, keep in mind that your cross-cluster traffic may be traveling over the public internet. So don't do this without strongly investing and understanding the mutual TLS or other encryption packages that are available to you. What this doesn't give us is the ability to have hard multi-tenancy for service mesh configuration or for service identity. Notice that cluster 2 is able to impersonate service B in this case. And if they were able to spin up a service with the same name as service A and namespace, they could impersonate service A as well. So this is not suitable for a hard multi-tenant environment, but potentially for different teams within an organization could be useful. It's also completely orthogonal to control plane scaling. You can run multi-cluster with one control plane, with 2 instances of one logical control plane, with 3 logical control planes across only 3 instances and 2 clusters. It's orthogonal. They move independently, and that's going to be customizable to your particular use case and needs. Also, we're talking a lot here about pods and clusters and things like that. This is KubeCon after all, so we're talking a lot about Kubernetes. But a cluster is really, from a service mesh's perspective, just a context for running compute. We have these 5 needs from a cluster. We need something that will run our control plane, will run our application, will make sure our data plane is running wherever it needs to run, sidecar, node agent, etc. Then we need something to tell us where to find a service, and we need something to hold our config. In some cases, actually, some service meshes come with that prepackaged. If you can satisfy those 5 goals, you have a cluster. It's not a Kubernetes cluster. Don't try to create a pod on whatever it is you've cobbled together. But the point is, if you're looking beyond Kubernetes, service mesh has a meaningful value there. And it's going to be difficult, but it's not that difficult. We can boil it down to 5 bullet points. How hard could it be, right? And so now that we've gotten up to the scale of multiple clusters, multiple control planes across logical and instance scaling, we've reached the ultimate abstraction, right? Well, I think there's one more level of detail that we need to talk about, and that is multiple meshes running concurrently. This is a little bit more abstract, and it's early. It's something that is not as well supported in documentation across service meshes as it probably ought to be, and as it needs to be as it becomes a more popular alternative. In this case, we've been sharing less and less and less as we move forward in our service mesh journey. We've been sharing no compute. We've been sharing no config. We've been sharing not even the same cluster. And within multi-mesh, what you're sharing is only trust. And it's not trust for a lot, frankly. It's just identity trust. When you scale to multiple meshes, you've got multiple clusters. Okay, no, they're orthogonal. You could theoretically run multi-mesh within a single cluster. Probably don't, though. You need that sort of logical separation of concern. You don't want administrators to have access to your cluster. The config could just get quite confusing. In this example, we've got services A and B. And within our prod mesh, these identities are specific. No one calling production service B should ever accidentally get routed over to developer service B, right? Developer could be whatever is at the tip of GitHub. Your results may vary wildly with how that performs. So these identities are completely mesh specific. There's no need to worry about naming overlap or anything between them, but they can establish strong trust between them. When service A receives a call from service B, it can be certain that service B is running in your developer environment. Service B, alternatively, can also be certain that it's reaching service A in your production environment. These also are sometimes useful crossing organizational or even company boundaries. You could expand your multi-mesh environment to allow identity trust across so many domains. Sorry, I got a little bit lost here. Thank you. You're not trusting anything other than identity. So service B has no ability not only to impersonate service B on the prod mesh, it also has no ability to change its execution. You can't overwhelm it with too much traffic. You can't change its application configuration or change the image that it's running against. There's complete and total isolation between these, and so you can have trust. Well, I hope that this has helped to clarify some of the dimensions. I hope that we can use these terminologies to discuss and compare and innovate as a field how service mesh meets the needs of our users. There are a lot of Googlers who helped me out along the way, and I wanted to acknowledge them. And now I have time for questions. Yes? Yeah.
So what does it mean in reality?
So the question is if we have any real world examples of where multi-mesh federation and trust federation have been used in production. And I don't have any of those available today. What you were talking about is, I think, at the bleeding edge of what service meshes have to offer. And so I don't know of any implementations. However, I mentioned that my boss preceded me. My other boss will be here after me. And that would be a great question to bring up to Louis as he comes to the stage.
Just what has transpired, or do you envision a scenario, real life scenario, where it can be moving forward?
Oh, do I envision a scenario? Sure, many enterprises utilize Workday. And they need to utilize Workday in a secure fashion. There are going to be HR systems that need to query the Workday API. And there's going to need to be data exports that come from Workday back to our HR systems. There's going to be a complex system integration for these things in place. What a multi-mesh could do for that is allow one single root of trust to guarantee to, I'll use Google as an example because I work there, to allow Google to certify that they are in fact contacting the Workday APIs, and the Workday APIs to be certain about exactly what service within Google is contacting them. Then they can set up RBAC rules to meet whatever their business needs are to say that the time off service has access to my PTO day API, but it does not have access to my medical benefits API, for instance. Google Assistant, everyone, isn't it wonderful? Any other questions? Yes? I'm sorry, I'm a little bit hard of hearing. Would you mind repeating a bit louder?
Sure. You mentioned on the slides that usually application doesn't know about service mesh. It's black box.
Yes.
Sometimes application knows about service mesh. Part of the traffic goes directly to your service, bypassing service mesh. Other part of the traffic goes to the service mesh. I'm just curious, what would be the use case of the participation that would be useful?
Okay, so to repeat the question, we're asking what is the use case for a white box data plane where the application is aware of the fact that it is being proxied by a service mesh rather than the black box case where we simply collect all the traffic and proxy it on their behalf. As I understand it, many of the Envoy-based service meshes have limited support for traffic like UDP. And so there are going to be cases where a single application needs to have UDP and TCP traffic. That UDP traffic, they would be able to selectively bypass the proxy and route it natively. I think that you could probably come up with other use cases where for various business reasons you may not want a certain particular piece of traffic to be a part of your service mesh while everything else should be. In that case, a white box solution would be appropriate. Any other questions? All right, well, I think there's a big panel. Save all the hard questions for them. And enjoy. Thank you for the opportunity.